Okay, so here's one of our examples for hybridization. And what we have to do first is we need to draw the orbital diagram. So let's do that. So phosphorus is Ne and then 3s up, down, and then 1, 2, 3, 3p, 3. Now, this is really special, all right? And this is kind of interesting. You know there's a 3D because we've been doing electron configuration for a while, all right? But you also know that we normally wouldn't use it yet, all right? Normally we'd have to go to like 4s2 and then back down to 3D, right? But phosphorus is special, all right? So phosphorus is one of these that it can access this d orbital, all right? And what we would call this is an expanded orbital, expanded octet, because it's going to use more, it's going to have more than 8 electrons in there. So let's check this out. So phosphorus has electrons in the 3rd energy level. And since the d suborbital starts in the 3rd energy level, it can use that to have more than 8 electrons in its valence shell. All right. So what happens is, just like the other ones for hybridization, this extra electron that would normally not be used in bonding can actually go over to the 3D. And what this would look like when it does that would be, all right, so Ne, it would be 1 up arrow. So we have our 3. S, we have our P's, right? And then we have 1, 2, 3, 4, 5, and these are 3 D's. Whoop, that's not a D. 3 D's, and then 1 there as well. So it would look like this, meaning that you could bond 5 things to it. Now, check this out. If we actually draw what phosphorus looks like, you'll see this looks a little odd. Phosphorus has 5 valence electrons. And we normally would draw it like this, right? And we would say, hey, you can only bond to the single ones. All right, so we would only normally bond to these, which is correct most of the time. The weird thing here is you can do this expanded octet with phosphorus, and you can actually bond to these ones as well. So what this would look like, this PF5 would be P with those 5 electrons around it, and you have a fluorine attached to some unexpected spots, like here, here, and then around it. And these are the expected ones. Now, it works with phosphorus because phosphorus is in the 3rd energy level, right? It's the 3rd energy level here. This would not work with nitrogen because nitrogen's in the 2nd energy level. It doesn't have access to the D's. There's no D's in the 2nd energy level. So you would end up with this here, and this has its own shape, but we're not going to talk about its shape this year. All right, we're going to keep to the 6 shapes we've already talked about. But the reason that's called an expanded octet is because if we were to count up all the electrons around it, we would see there's 2, 4, 6, 8, and then 10. So there's 10 electrons in its valence shell because of this weird expanded octet. All right. And it does that same kind of thing that we've seen with the other hybridization, where it just shifts over by 1. All right. Okay. Any questions with that? All right. There's one other odd one, and it's right next to phosphorus. It's sulfur. So let's check out sulfur. We have sulfur, Ne3S up, down, and then 3p, 4. All right, so this does the exact same thing that phosphorus does, but it does it twice. It's the same reason. Phosphorus, oh, I didn't even change the name when I gave this, when I copied it over from the last one. So sulfur has electrons in the 3rd energy level, and since the d orbital starts in the 3rd energy level, it can use that to have more than 8 electrons in its valence shell. This is also called an expanded octet. So what we have now is we have that shift, because remember, there's another D here, and it's just empty. All right, so now what's going to happen is you're going to move those electrons over. One's going to go over here. One's going to go over here, and then you'll be able to bond even more. All right, so let's write this out. So I'll keep the color. So we have 3s. Now it would just be an up. We have 3p, up, up, up. And then we have 1, 2, 3, 4, 5. 3d, up, up, because we moved 2 over. Now, just like the other one where we combined the energy levels, the same thing's going to be true here. Because we're dealing with 1s, 3 p's, and now 2 d's, we would call this an sp3d2 orbital, all right, because it's hybridized. It's all kind of come together. So the same thing's true with this last one we did. We would call this one an s, because there's an s here. So s, there's 3 p's, so p3, and then d. So this would be called an sp3d orbital. And that would be the name for this one. Now let's draw this down at the bottom. So sulfur has 6 valence electrons. So we have 1, 2, 3, 4, and then 5, and then 6 here. And you can see that there's going to be 6 fluorines that can attach to it. So just like the last one, we would do the same thing. We would just put fluorines around each of those 6 electrons. And then this would have its own shape and name and all that kind of stuff as well. But again, this year, we're not going to focus on that. I just want to show you that it's possible to do this expanded octet. So we talked in the beginning that there's incomplete octets where it doesn't get up to 8. And then there's expanded octets like this one where it gets above 8. So let's figure out how many we have here. We have 2, 4, 6, 8, 10, 12. So we have 12 electrons in its valence shell, which again is above the expected 8. All right. And fluorine would be the example for this. I'm sorry, sulfur would be the example for this. Oxygen, even though oxygen looks the same because it's like this here, oxygen's in the second energy level, so it can't do this shift because there's no d orbitals in the second energy level. So it's restricted to not being able to do that. All right. Okay. So that is the basics of hybridization. And the key with it is understanding this up here where you do the electron shift so that you can get more electrons that are all up arrows so then they can bond to more things. All right, that's kind of the key with hybridization.